Good morning viewers to the interactive session on computer numeric control of machine tools and processes. So, I welcome you all and I would really like all of you to participate by sending us questions. I will first start with the questions that you have already sent us, and in between you can send us questions or queries or doubts that you want to be cleared, so that you can proceed on your own with the leftover assignment and also with the final exam. So, let us start formally. I will start with the questions. Be ready on your side to give us any questions that you would like us to respond to. So, one student says more explanation should be there in digital differential analyzer, which is the working unit of hardware interpolator in CNC. First of all, this aspect of digital differential analyzer has a very good book which you can refer to. It is available in most of the libraries, and it is also available in commercially it is available, you can purchase it also. It is Yoram Corain, Computer Control of Machine Tools. We regularly refer to this book for references in these chapters. So, let us start. What we have basically introduced is an adding circuit. What is the necessity of this adding circuit? The necessity is this, that in many applications in CNC machines, we require different frequency pulse trains, but when we are looking at the input side has a fixed frequency pulse train, which is called the clock frequency. This is generally like the clock frequency which is available with PCs, and we compare the fast working of PCs, I mean how quick or how fast a PC works by comparing their clock frequencies. Something might be having 3 megahertz or 3 gigahertz, etc. These things indicate how fast it can work. So, this frequency which will be provided, this very high frequency might not always be the frequency that we require. Why do we require different frequencies? Because many times what happens is we are driving motors with a high frequency pulse train, and this needs to be variable in order to drive motors at variable speeds. So, I want the first requirement that we identify is that I require different frequency pulse trains for driving motors at different speeds. Why do we require different speeds? Because in point to point machining we never require different speeds. I require different speeds because in continuous control I might have different speed combinations for cutting along oblique lines, for cutting circular paths, etc. on the CNC machine. The x axis and y axis velocity values might well be different, and that requires that I have different frequency outputs from this device. How does this device operate? It has defined with it a particular number of bits of these counters. As I have written here, you will notice that it has n bits and it has x, x as the binary number inside. There is another counter just by the side of it, and this plus sign indicates that this x is going on getting added to itself, again and again to finally accumulate the result here. So, what happens is x is getting added again and again, and f is the input pulse frequency, and the output pulse rate which is obtained here is equal to f into x by 2 to the power n. Now, as this discussion will be quite elaborate, let me directly move on to its derivation and its application. Second, so if I give 2 to the power, if I make 2 to the power n additions of a number 1, it will result in 2 to the power n, which exceeds the capacity of this particular, let me show you. This exceeds the capacity of this one. What is its maximum capacity, maximum number it can hold? The maximum number is 2 if you look at this paper, 2 to the power n minus 1, which means that if n is equal to say 3, then 2 to the power 3 minus 1 is equal to 7. It can hold a maximum number of 7. Second, if n is equal to 4, 2 to the power 4 minus 1 will be maximum 15. So, it can hold a maximum number of 15. And how does it look like? It looks like this: 1, 2, 3, 1, 1, 1, 1. This is the maximum number it can hold inside, and that is equal to binary 15 is equal to decimal 15. Okay. So, this means that I can have a maximum number, and after that whatever number is getting accumulated, that will overflow. What is that? For example, suppose I add 1 to it, so that this will become 0, 0, 0, 0, 1. There is absolutely no space provided for accommodating this 1, and this 1 goes out as the overflow. This goes out as the overflow. This is the basic idea. So, let us now quickly move on through the derivation. So, 2 to the power n additions of the number 1 gives rise to 1 overflow. So, if I have x added to itself instead of 1, so the less number, proportionately less number of additions will be required. So, 2 to the power n divided by x additions will provide 1 overflow. So, by unitary method, if these number of additions provide me 1 overflow, 1 addition will provide me with this much overflow, this one just inverted. So, that means f number of additions, which means f being the frequency of the pulse train coming in, with every pulse of the pulse train one addition is taking place. So, with f number of additions of x value, f into x by 2 to the power n overflow pulse rate will be obtained. Okay. If you have doubts in following this one, just ponder over it when you have some spare time, and I am sure you will agree with us. So, this is our magic number, the rate equation. Next, I have shown you by actual addition how this overflow can take place. I am having say x equal to 3, 3 is being added to itself again and again. So, first addition 3, second addition 6, third addition, and what is the size of n? N is equal to 4, n is equal to 4. So, it can accommodate maximum 15 or 1, 1, 1, 1. So, 6 plus 3 12 plus 3 15. So, it is filled to capacity here 1, 1, 1, 1. Next one plus 3 18, 18 is equal to 1, 1, 0, 0, 1, 0. That one overflow is lost, it cannot be accommodated in 4 bits. So, that goes out as the overflow, and what is left here inside the counter? 2. Okay. So, 16 goes out and 2 is left behind. So, next again with 2 you add again 3, you get 5, 8, 11, 14, 17, again another overflow. But the rate is not absolutely uniform, because there are 5 additions here and there are only 4 additions here, creating these overflows. Why does this happen? This slight discrepancy, because you are not always starting from 0, you are starting with a leftover. Why not cut off the leftover? In that case, proper integration will not take place. Okay. So, this way you can have overflow pulses coming out at regular intervals, and you can make it absolutely regular, I mean more regular, by increasing the size of the counter. Then it will become, this rate will become, overflow rate will become more and more uniform, etc. And this one shows how we actually design that interpolator. Once you understand that this output is f into x by 2 to the power n, in that case we have a combination of these, and this is elaborately discussed in the lectures. Now, with the basic idea of the interpolator unit, the DDA, now that I have given you a rough idea once again, please see whether you can follow the lecture once again and come to the conclusion, I mean agree with our conclusions. If not, you can give us a feedback here itself now, that please describe this part also. I will definitely do that. Okay. But for the time being, with this initial discussion, if it helps you to follow it now itself, fine, otherwise give us a feedback. So, I am skipping this for the moment. I also had a numerical problem worked out here for you to have a look and share with you. So, I will do that if you give us a feedback through the screen. I think we are not having much feedback from the screen. Is everything all right here?
Yes, sir.
Okay. Another student has given a feedback in the sense he is saying, I didn't understand how to solve problems from 6th lecture videos. 6th lecture videos. So, I have brought a copy of all the questions that we have discussed. I will definitely discuss some questions from the 6th lecture. 6th lecture, MCQ 1. Let us quickly have a look what we are discussing. All right. So, let us start with question number 1. What is the purpose of using recirculating ball screw nut mechanism in CNC machine? Is it to reduce the setup time? No. For higher surface finish? No. For carrying out up milling? No. To remove backlash? Yes. Backlash is removed by recirculating ball screw nut assembly if the balls are slightly oversized and some preloading is applied. So, answer is the last one, to remove backlash. This one pertains to the last week of lectures. So, I will skip this one. It's actually very simple. Achha. So, in the meantime, we have got a feedback that which book should be followed in order to get a better grip on the subject. So, I will quickly check whether I will go forward a bit. I think I have made a list of books. Please bear with me. Oh no. Okay, I can give you the books here itself. Please bear with me for a moment. Right. Right. The books are, first is for computer control. This is the best book that you can have in the market. Computer Control of Manufacturing Systems, followed by closely by P. N. Rao, CAD CAM. It might be CAD CAM and numerical control, etc. I don't remember the last part, but if you put this on the internet, it will definitely confirm what's the full name. P. N. Rao. This is also a very good book. You can follow this. There is Kundra, Rao and Tiwari. And about numerical problems, as you have mentioned, for more practice on the problems, Yoram Kuren is having some questions in its chapters. I have not covered the questions in all chapters. I will definitely not give you questions which have not been discussed at all in the lectures and the assignments. No foreign questions. So, if you find that there are some questions in Yoram Kuren which they are absolutely new to you, please be rest assured I will not surprise you in the final exam. So, questions which are in Yoram Kuren which are related to our lecture course topic, that you can practice. Kundra Rao and Tiwari is a very good book. It is called Numerical Control and Computer Aided Manufacturing. Next you have Michael Groover for all the things which are dealing with digital logic, digital control, etc., etc. Okay. And say Rogers and Adams, not Rogers and Adams, the notes that I have provided you for DDA, interpolator and the notes that I have provided you for surface machining, please follow them. And also, if you are interested in more problems, you can refer to the assignments which had been solved for the previous run of the course. I am not sure whether they are freely available to everyone, but this had run previously. So, it will have assignments 1, 2, 3, 4 for the previous run. It will have question papers 1 and 2 for the previous run. So, that will give you quite a lot of practice if you are inclined towards that. If you cannot spot these previous assignments and question papers on the website of NPTEL, then please drop me a mail. I will try to get them and I will put it up in the forum. Okay. This question, the following surfaces can be machined on. So, this is a free form surface. It can be machined on CNC milling machine. It cannot be machined on CNC lathe since it is not a surface of revolution. It cannot be done on the conventional lathe and neither on the CNC turning center. So, answer is CNC milling machine. So, you have said that you are facing problems with these questions. So, now that we have discussed two, I can understand that many of them deal with concepts instead of numerical problems. If you are facing problems over the concepts, please go through the lectures once again, because if I try to discuss each and every problems, there are 20 odd questions MCQ, that will take time. Okay. So, let me spot 1 or 2 questions in between, I will discuss them and then again wait for other students for their queries. So, let us see, in a CNC machining center, any complex cutting motion involving x, y and z axis movements is carried out by. So, it is basically asking how do you get the motions? Use of jigs, cams, templates and tracers? No, because in that case it would have been a simple hard automation example. Hard automation means when you are getting automatic motion with the help of physical devices which are referred to as fixed automation or hard automation, which is difficult to change. So, first one, no. Skill of the machine operator? Definitely not. That is exactly the opposite of CNC machining. So, not even B. Combination of movements obtained from motors along the axis? Yes. And let us see, there are other options also. None of the others, definitely not if C is a good candidate. Using specific gearbox settings that distribute the power to the axis. This is not correct. I will say this is not correct, meaning that complex cutting motion is not obtained this way, but there are many CNC machines in which gearboxes are still there. Why is there some gearboxes? Because sometimes you have a high range speed and a low range speed and they cannot be obtained in a single setting. So, there is a gearbox which can be operated from the program itself. You shift a clutch which connects you up either with the high range set or the low range set, but for complex cutting motion gearboxes are not used. So, answer is C. Acha, this is also another conceptual question. Let us have a quick look at it. A machine will be said to have CNC control if the dimensions of workpiece are measured by sensors while cutting goes on. No, this is online monitoring. Online monitoring and or in process gauging. In process gauging is not necessarily CNC. Okay. The tool motion is guided by drum cams and disc cams. Definitely not. This is cam controlled machine. The loading and unloading of the workpiece on and off the machine respectively is made automatic. No, this is not sufficient for a machine to be CNC. Loading and unloading of the workpiece can happen, but the machine is not necessarily CNC. Control is achieved by employment of alphanumeric data. Yes, we generally use alphanumeric data, that means letters, numbers, etc. in a form of a code, and we achieve control. So, for this one D is correct. Acha. In computer control machine tool terminology, a machining center is machining center. So, we are asking what is a machining center? The origin of the machine coordinate system with respect to which the operator has to make his program. So, they are referring to the origin of a, just like a graph paper has an origin. So, that point, no, machining center is not that. The center of the cutter which actually goes to the program point, definitely not. A computer controlled machine tool capable of a variety of operations involving rotating cutters, this is the one. Shopping center, machining center, they all have the same idea, that is a central place in which a number of machining operations they are available. Just like shopping center is a central place where a number of shops are available. So, question number option 3 is correct. So, let us quickly go through some others. In computer controlled machine tools, tool movements are controlled by, these are now of a same pattern, definitely not machine operator, definitely not cam, definitely not foolproof mechanism. By the way, what is foolproof mechanism? Foolproof mechanism means that even an ignorant person will not make an error while operating in the presence of the foolproof mechanism. What kind of? The foolproof mechanism will ensure that you will not connect up, say in the lathe, you will not connect up the feed rod and the lead screw together. You will not connect up the longitudinal feed and the cross feed together. There is absolutely no possibility. Okay? So, exclusively you can only use lead screw, or you can use feed rod, you can only use longitudinal feed, or you can use the cross feed, like that. But tool movements are not controlled on the CNC machine by foolproof mechanism, no. So, answer is none of the others. So, I will skip some questions. Okay, let us have this one. Holes are to be drilled on the circumference of a circle with regular angular spacing. If a CNC machine is used, it should essentially have one indexing head. Answer is no. No physical devices have a CNC rotary axis of motion to rotate the table about a Z axis. No, why have physical devices when you can simply name the axis points to which the tool should be reaching? Be a CNC milling machine with, I am sorry, but somehow it is not accommodated within. It is my fault really, maybe I made a mistake with the font size. The answer is, if a CNC machine is, it should essentially simply be a milling machine. No, it need not have contouring also. I cannot see the other options, sorry, but it need not be a milling machine with contouring features. No, it can simply reach these whole points if you mention the coordinate values. Sorry about this. Okay, so now I will skip a number of questions and go for, okay, let us try this one. What is this? For milling a bilaterally symmetrical 2D profile, bilaterally symmetrical, okay, on metal plate 10 millimeters thick, a milling machine would require the following. So, it says if something is the same geometry is there on two sides of an axis, in that case what do you require? Do you require copy milling attachment? There is a CNC machine, mind you. No, no copying on the CNC. Dividing head? No. Reversing table? Do we really need that? I mean, do we really need it? Because it says that would require means it will necessarily require it, otherwise it cannot do it. No. Reversing table, that way is not necessary. Rotary table? No. Simply we can use mirror imaging. This is the answer to the. So, as I am saying, the concepts are very simple, but I have given it in such a way, I have hidden the truth, so that you might have to be very sure to tick the correct answer. The answer is none of the above. You do not need any one of them, but you simply require mirror imaging. In order to produce a circular groove by milling in CNC machining center, a universal dividing head, now that you have got the hang of it, no physical devices. The moment you see something like dividing head, cut it off. CNC does not require it. Planetary gear mechanism, no mechanisms. Rotary table, not even that. The milling machine table is able to combine X and Y motion in such a way that the tool will be having relative circular motion with respect to the job. Table does not rotate. There is no requirement for the table to have pure rotation about an axis, no. So, now I will skip most of the questions and come to, okay, what does this say? A XOR B is equal to, this answer is A dash B plus B dash A, okay, A dash B plus A B dash or B dash A, the same thing. So, the third one is correct. So, I will now skip these questions. I will definitely come back to you if you give us such a feedback or if you send me a message, because so many of these questions are there. We will be spending our useful 1 hour attending to, oh my, it simply does not, okay, there is, this is something different. sorry. Let us come to some of the interactive questions which are given by the students. So, which book we have already covered? Explain the possible ways to control the basic length unit. Very good question, I would say. So, let us take the example of, first of all, the point to point open loop system. So, I will write on top point to point open loop system. In the point to point open loop system, you have the stepper motor. I am drawing a block diagram, nothing, just schematic. It deals with the gearbox. This one deals with the lead screw nut. So, lead screw I am writing like this, and the nut on top of it, nut, and here you have the table. So, let us see how can I control the basic length unit. Basic length unit, is it dependent upon the frequency of pulses? Absolutely not. The table will become faster or slower if you change f, but it has no effect on the basic length unit. So, f is out. What about the stepper motor? Stepper motor is just working like a passive servant. So, here what happens is the lead screw and the encoder, only these elements can affect the basic length unit. The gearbox cannot do it. It is simply the relation between lead screw and the encoder which defines the basic length unit. So, the same thing applies in case of continuous control. So, now that basic length unit, f cannot, okay. F is the pulse generator frequency, pulse generator Hello, can you hear me, friends? So, I hope you have not missed. I hope all of you are able to listen in. So, let me continue. I will just repeat the last part of the question. I mean, the last question answer to that I will repeat. What we have discussed basically is this. I will bring that paper down again, I mean back again, and you will find that here we have discussed in the point to point open loop, the basic length unit is only affected by the gearbox ratio and the lead screw, what do you call it, the lead screw lead value. How does the stepper motor affect it? In absolutely no way can the stepper motor affect it. Only one case it can affect, if it is run in half step mode. If it is run in half step mode, then only it can affect. That means, instead of executing 1.8 degrees, if it is run at 0.9 degrees or some other fraction by some other means, only then it can affect. Frequency of pulses, no. In case of point to point closed loop, the gearbox, even the gearbox cannot affect it, only the lead screw lead and the number of holes on the encoder, they can affect the basic length unit. So, this is the part of the discussion, unfortunately did not reach many of you people because of audio, suddenly audio connection got lost, but now I hope that all of you can listen to me and this part of the question is cleared. Okay. So, now that we have some time, I will just wait for further questions which you might be having. So, please feel free, otherwise I will come back to the questions which have been asked by you people in the through the Google pages, shared Google pages, and some students have written any best book for CNC programming. So, CNC programming, the Yoram Cohen book is not good for programming. CNC programming you can refer to P. N. Rao's book, P. N. Rao, that is good. Kundra, Rao and Tiwari is also good, Kundra, Rao and Tiwari. Okay. And somebody has said that please simplify the course. I understand, and he has also commented, he or she, whoever, very complicated course for graduating students. I agree with this, because as much as possible I have tried to convey concepts instead of giving general discussion. See, since most of you are going to become engineers, so your target should be that you should you should be at the concept level, but if you are only learning how to operate the machines, then your full faculty, full capability won't be utilized. So, as much as possible I have tried to deal with the concept part, and I have tried to deal with all aspects of the concept, not only programming, but further developments like surface machining, what is going inside the machine, everything I have tried to cover. So, it might seem to be a bit difficult, but maybe later on if you are still in this line, maybe you will feel that yes, somehow the course has helped. Okay. So, forward step, let us look at what is the forward step. So, if you look at a free form surface, we have generally discussed this way, that if I am trying to cut this surface out of a block of material, in that case generally we are selecting in a 3 axis. So, these are the things which need to be kept in mind. 3 axis machine, say a machining center, and we are essentially using a ball end milling cutter. So, you have flat end milling cutters, you have ball end milling cutters. Why are we using ball end milling cutters? Because if you have concave points in the surface, suppose this surface is like this, a flat end milling cutter won't be able to get inside. Because of this simple geometrical reason, we are using ball end milling cutter, but then also we have to be sure that the radius of curvature defined by the ball end should be it should have a smaller radius than the radius of curvature of the concave portion, otherwise you cannot get inside. So, first essential thing is that use a concave milling cutter and then start moving it to and fro. Now, is this the only way to cut? No, definitely not. You can also move by spiral, that means you go on cutting this way. You can cut this way and get the shape, but we have to a large extent we have restricted our discussion to and fro motion. That means go for a zigzag type of motion or go from one side to the other, take a side step, go again straight, like that. These are called these paths are called the tool paths, and these tool paths, though they look very smooth, they are actually consisting of small straight line segments. Why straight line? Because that is the easiest thing that we can do. If you try to cut in a circular manner or along parabola or ellipse, you will be bringing in more difficulty for yourself, and the CNC tries to maintain accuracy by reducing the segment length. So, it keeps the whole thing simple by making them straight lines, and if more accuracy is required, it goes on reducing these particular forward steps. So, forward step is defined by small straight line segments which make up the to and fro cutter paths in surface machining. This is the formal definition. And what does it depend upon? It depends upon how much is the curvature. If you have, suppose you are seeing in 2 dimensions, if you have a highly curved surface, in that case the forward step cannot be much, because if you take large forward steps, you will have lot of deviation from the actual surface. Okay. Here you are not having much deviation because it is almost plane. Here you are going to have lot of deviation, here you are going to have lot of deviation. So, forward steps are essentially function of the local radius of curvature of the surface in the direction of the cut. Okay. So, I hope that gives you a good idea of the forward step. If you still have problems, oh, and I should add something, this distance can be defined to be, you can make calculations for finding out the length of the forward step by keeping this within a limit called the form tolerance. That means how much maximum deviation you can tolerate, form tolerance. So, if you are taking very large forward steps, not bothering much about how much deviation you can be tolerated, then you are violating the form tolerance criterion, and there will be inaccuracy in the form. So, surface finish is not much affected, but the form is affected. Okay. So, I think further questions have not come in. So, I will again revert back to the questions which have been posed by students in the Google page, shared Google page, about controlling of robotic arm motion. Robotic arm motion is a bit more difficult than this, because it might might go for combined action of a number of motors. Okay. Number of motors will be involved, and you might have more than one option to reach a particular point, I mean target point from an initial point. So, there are lot of other options which I have not discussed in our class. We have restricted more or less to the discussion of CNC machine tools, that means machines which are generally used for metal cutting. Principles are the same, but there you have some consideration of more prime movers, and therefore, you have more options to reach a particular point, and therefore, other criteria they come in, which I have not discussed in the lectures. Okay. So, this I will not bring in at this moment, since it is not part of the basic course. The next question was, does a 3D printer come under the category of CNC machines? Yes, very much. If you are considering in a more generalized form additive manufacturing requires a very good control of the XY table with ability to move selectively, so that only part of the table is covered by whatever deposition process you are having in mind. You also might have to control the tilting of the table if you are having multi-axis deposition in mind, and you also have to control the z-axis motion to define the layer thickness which you have in mind. So, for layer thickness, z-axis motion, for the profile of the section that you are consolidating, x and y motion, and rotational motions for controlling the tilt which might be required in multi-axis deposition. Any best book for CNC programming? I have already mentioned. P. N. Rao is possibly the best book. Okay. So, one more question has come in. So, let us have a look. More explanation about definitions in GTL. Okay, in GTL I can give you a quick top up on the definitions, in the sense let me take in fact one or two definitions which will cover the basic principles. Once the basic principles are clear to you, you will be able to deal with any definitions. Let us take this one. I have an existing circle defined this way, C1. I have an existing straight line defined this way, L1, and I have the task of defining, this circle which is touching the straight line, touching the circle, and having this particular direction. So, I have to define this. What is given about this? It is touching the straight line, it is touching the circle, it is having a particular radius of say R10. This is my task, I have to define this circle. So, you might say what's so difficult about that? You just define it using the definitions of GTL, but the problem is there are 16 such possible circles that can be drawn satisfying almost all the conditions. This one is touching the circle, touching the straight line, this one is doing the same, this is doing the same, this, and their directions can be this way and that way. So, that makes it 8 into 6 to 16 possibilities. Now, what are the conventions in order to define it? We define it this way, if you are conversant with driving along one way routes, you will immediately understand the idea. Think of two routes to which this defined geometry will be forming a shortcut, that is it. So, how will it define a shortcut? It is having a one way route. So, it can only be defined, you can only drive your car along this route. So, this one is a shortcut, okay, from this point to this point. You might say, why did not you consider the other side, this one, to be a shortcut? It is definitely not a shortcut, it is a long cut. Okay. We only deal with minor arcs for definition. So, this is broken up into major arc and minor arc by these 2 points of contact, and we only involve the minor arc for definition. This is rule number 1. So, we involve this one for definition. So, question is, you ask yourself, to which two roads, one way roads, does this form a shortcut? So, you will immediately say, why? You drive your car along this path. Suppose this is your car, you are driving this way, drive your car along this path and end up this way, that is it, that is the answer. This one is minus C1 and this is minus L1. So, the definition will be say this is C2, just a moment. C2 is equal to, you are driving along minus L1, so that comes first. Next you are landing onto minus C1, that comes second. So, these are the two roads that you have mentioned, and this one is counterclockwise circle that you want to define. Counterclockwise is radius with a positive sign. So, you give R 10 or R plus 10, this will be the definition. So, what are the conventions that we have learned? The conventions are, at the points of contact, in order that this will be providing smooth passage of the car from this road to that road, the directions of these geometries must be the same. minus L1 is having this direction, C2 is having this direction. So, the direction matches at this point, direction matches. At this point minus C1 and C2, the direction matches. Okay. So, minus L1 to minus C1, this provides a shortcut, a real shortcut. This is a minor arc, and this gives the direction of the circle counterclockwise. So, all these will merge to give only this circle, no other circle will satisfy all these conditions. Okay. I hope this gives you a good grip on the conventions that you have to take. Matching of direction at the points of touch, next minor arc to be involved, next direction of the circle should give one way route of the shortcut, that is it. All these conventions will help you to choose the correct option. So, please you can get back to your definitions again and see whether this clears your doubts. If not, you can definitely approach us once again, if not now, then through the forum. Okay. So, if we have more questions coming up, before that let me quickly have a look at the questions that have been posed by different students. One student has said that he would like to ask about CNC machines controlling unit with PLCs. This is a very good question. I am sorry, I did not cover anything about PLCs, but PLCs are an integral part of many control systems, not only CNC. Let us see what is their basic idea. Basic idea in my own simple words will be replacement of replacement of hard logic with soft logic. Now, what does that mean? It means that you might have hard wired logic circuitry, you might have electromechanical devices like relays, etc. If you can replace these by language, that means soft logic. Okay. If you can replace these by programming, you will be making a lot of saving of removal of hardware, removal of wiring and all these things by simply introducing programming instead of hard wired devices. Let me give you an example. Suppose there is one signal A coming here and a signal B coming here. Lots of problems we have solved in the during the lectures, and suppose I make a condition that only if A is 1 and B is 1, then only they will be lighting up, say, a bulb. Then C should be 1 and it lights up a bulb. This is a hard wired logic circuitry. That means this one will be available in the market on a chip. Okay, this will be available on a chip and you have to give power to it, 5 volts power or maybe whatever voltage it asks for. There will be a pin out, that means there will be pins to which you have to connect up A, you have to connect up B, and they will be ANDed. There will be an AND gate on this chip and it will have an output point or output pin, and this has to lead to the circuit which will be ultimately putting this bulb on. So, if instead you can have a device in which this one is replaced by software. In what way? Suppose you receive this input and call it A, you receive this input, you call it B, and you have a line in the control program as if A is 1 and B is 1, then put C equal to 1. That is it, a language, a line instead of a hardware circuit. This will save you from having a hardwired circuit. If you require changes, you can change that simple line instead of changing some hardware circuit. Okay, this is the basic idea of the PLC, and PLC, that way electromagnetic devices, a number of them have been replaced by PLCs. It is language driven, so that if you want to make changes, you can make changes. The cost of and the hassle of rewiring and all these things are completely removed, and it becomes much more flexible in handling. The only problem is that in that case we have to have proper sensors by the help of which we can sense A and B, not only binary, such simple binary things, but you might have to sense analog analog signals. I give you something like, say, from a thermocouple or from some other device like that, you get 0 to 5 volts, any value, 3.5, 4.5, 4.72 volts coming in, and you have to sense it. Now, how do you do that? If you cannot do it, that input is useless to you, you cannot use it. So, for that you have to be sure that your programmable logic controller, as they are called, let me show you some figures here. This is an electromechanical device, you know, it is spring loaded. This one can move like a seesaw up and down, and it can either contact this point or contact that point. And here you are having a magnetic coil, where if you energize it, it pulls this body, say made of iron, it pulls this body, and this part it contacts this side. Otherwise, if it releases, if there is no energy given to this coil, it releases, it does not pull it anymore, and the spring pulls it up and it contacts the other side. So, this is an electromechanical relay. This can be replaced by PLCs. So, PLC inside the programmable controller does a lot of logic operations, takes in inputs and sends out an output. Everything inside can be done by software. Okay. So, the functions are detailed here. It can control relay functions, timing, counting, arithmetic, all these things we have done ourselves, but these are integrated inside a single unit called programmable controller. Okay. So, I think some new questions have come out. Let us have a quick look at them. Yeah, some explanation about isoplanar method. Isoplanar method essentially deals with a method in which you have a surface, free-form surface, see it is like this, and we have to generate cutter paths. Problem with the isoparametric method is that though it is relatively simple, if it has an irregular shape, then you know the cutter paths will be clustered on one end and they will be spread out on the other, so that roughness will be very low on this side and quite high on that side, so that there will be non-uniformity in roughness, which is not good for many engineering applications. Suppose this is going to be dipped under water and it is supposed to act as the aerofoil profile of a submarine wing. In that case, different type of liquid behavior will be found. Where you have low roughness, there you might have laminar flow, where you have high roughness, maybe you will have turbulent flow, and suppose that might create some problems. So, many engineering applications require that you have uniform roughness everywhere, and for that we generally have a method called isoparametric. But in between these two lies the isoplanar method, where if the radius of curvature is not varying very much, in that case it acts as a good choice for restricting the roughness within certain limits. What is that method? Suppose this is a piece of cake and you want to cut it, or this is a loaf of bread. So, you will take your knife and make a vertical cut on it. So, if you have many friends, then you have to make many such cuts, and you will be careful to make these cuts parallel to each other, and they will come out like this. Now, someone might say, parallel to what? So, this is your knife path. So, it is basically a vertical plane. So, wherever these vertical planes cut the surface, you are having intersection lines, and those very intersection lines are your cutter paths. Okay, what good do we gain out of it? If we look at it, look at the surface from the top, we will find that these lines are parallel to each other. But does it give us equal roughness? No, because equality in roughness will only be obtained if you have same radius of curvature of cutter, equal side step and same radius of curvature of the surface perpendicular to the path of the tool. Radius of curvature of the surface you have no control, it can be just anything anywhere. So, that one will still create non-uniform roughness, but you can limit the roughness by choosing this particular side step. At least the cutter paths are not going to limitlessly diverge or converge just like they have done here. So, at least they will be equally spaced. This is isoplanar method. In isoplanar method, I have discussed elaborately the way to determine the forward steps. So, I will urge you that please go through that discussion, because if I discuss it now, I will be saying the same words. So, instead of that, you can go back to that discussion of forward step determination in case of isoplanar method. I am sure with this introduction that we have discussed, it will be easy for you to follow it. If you have problems, I will definitely come back to that. So, coming back to our original discussion. So, if you are interested to have some more details about programmable logic controllers, these are some very good books which you can refer to, especially this second one, Michael Groover, Automation, Production Systems and Computer Aided Manufacturing. Maybe it is this book was in print some time back, and maybe it has been ousted from the market by the first book, because I find a common author. But if you can get hold of this one, I will definitely prefer that to be the case. Okay. Achha. So, so these are some of the discussion. Yes, this will be quite useful. What sort of input devices are we talking of? If they are binary devices, that means two state inputs, then typically the programmable logic controller can take these inputs. What sort of? Push button. Remember, there are some switches in which you have start button, stop button. If you press the start button, it is energized, it is on. If you press the stop button, stop is supposed to take place, the motor or whatever, that is supposed to stop. Photo detectors, just like in encoders we have studied, limit switches which define the limit of motion of a particular slide. If a limit switch is getting pressed at the end of motion, either the motor will be disengaged or maybe reversal will take place, as you wish. That particular option can be chosen by the PLC. Say in one case you want to choose reversal, so you can program for that. In another case you want stoppage of the motor motion, you can go for that like that. Timers are similar to say encoders, giving at regular intervals it is giving pulses. So, this way all these things we have discussed in some aspect or other, and these are typically outputs. Achha, these things that we are discussing, they are very simple things, in case they are basically of on off type, so that they can be represented by binary signals. So, a switch getting on, or what do you call it, the previous list, switch getting on, limit switch getting pressed, timer sending a particular signal after a certain time, okay, circuit getting broken. All these things are simple type, and they are easy to represent and easy for the PLC also to sense. If you can send voltage or no voltage, they can easily be recognized. So, these are not very difficult. These outputs are also not very difficult, motor getting on off, lights getting on off, etc. But the thing which is difficult, this is a typical ladder network which is used to represent typical types of circuits which you would like to exist. For example, say there are two switches in series and they are controlling a device called Y. Say this is a fan. Only if both these switches are in on condition, the fan is going to run. Okay. So, this will be the typical representation. Okay. Now, I have got another question from another student called this question is, please explain about Bezier surfaces in detail. What are Bezier surfaces? Bezier is the name of the particular person who gave this concept, used this concept to devise a surface. How does it look like? If you consider the Bezier curve, the Bezier, so Pierre Bezier was the person. So, this is a typical Bezier curve, say. How does it look like? The starting point is shared between the starting point of the curve and a point called a control point. So, let me say B0, Bi represents the control points. So, what is the role of these control points? The control points are essentially points which define the profile. Are they lying on the profile? Not necessarily. A control point might be here, next one might be here, this one is B1, next control point might well be here, B3. I mean, not exactly, my drawing is not very good, but the last point once again has to be shared, B3, B0, B1, B2, B3. Suppose we have drawn 4 such control points. In that case, how are they affecting the curve shape? Suppose this B2, I suddenly take it to this point. B2 is taken to this point. This is the shift. So, in that case, we will find the curve shape might go and change itself to this one. Why is this happening? Because the positions of the control points are going to affect the Bezier curve shape or the Bezier surface shape, but they are not necessarily going to lie on the surface. When the Bezier surface or curve, it is easy to understand the concept with the curve first, and then you can apply the idea for the Bezier surface. In case of the Bezier curve equation, it looks like this: weight 1 into control point 1 plus weight 2 into control point 2, weight 3 control point 2 and weight 4 control point 3. Okay. So, these weights are different for the different Bezier control points. Okay. How do we define these weights? So, initially we can see that it is a summation. Every point on the surface of the curve, on the curve is every point is a summation of the effects that the control points have on them. So, what is the exact nature of this one? It is a function of a parameter u, function of a parameter u. In what way? Suppose I draw this curve here. This is a curve. So, a parameter u varies along the curve, so that u is equal to 0 here and u is equal to 1 here. So, in between, say if you come to the middle of the curve, u will be equal to 0.5. So, u will be equal to 0.25, like that, as simple as that. What is the advantage? We will be utilizing this variable to define any point on the curve, just like we utilize say x to define any curve y. I can have x axis, I can have y axis, and I can define this particular curve as y is equal to a0 plus a1x plus a2x square plus a3x cube, which we call the polynomial. But we are not doing it here. It has a definite number of advantages if we do not do. Are we still having the x and y coordinate? Very much so. Here we have y and x axis, we have y and x axis, but we are using this particular u. Then if we are interested to find out any y and x value of this particular curve, how do we do that? There we are saying it is equal to a summation. What sort of summation? It is equal to I is equal to 0 to say in this case 3, and after that what do we have? We have the control point Bi. So, B0 will come, B1 will come, etc., etc., etc. And then we have NCI u to the power I 1 minus u n minus I. You might say that this is too complex. I will never expect you to remember these things for any question in the exam. Please understand that Bezier surface is something which which we are taking as something which we require for our CNC concepts, but I will not ask you any quiz that okay, I am giving you 3 control points or 5 control points and what is the effect on the Bezier surface. No, it is pointless, that is not our goal. So, let us quickly see what it is giving rise to. it is giving rise to this part which is a function of u. What is it called? It is given a name called Bernstein polynomial. What is its basic feature? Its feature is that it is a polynomial in u. So, now comes the explanation. Instead of polynomial in x, we are having x and y defined as a polynomials in terms of a completely different third variable. So, this is the advantage of Bezier surface. I am removing as the variable any x and y, I am bringing in a third variable in terms of which we are expressing this particular x and y. I will get x and y coordinates here. Who will lend me these x and y values? The control point x and y values. They will be multiplied with this particular polynomial, and I will be setting a particular numerical value for u. So, this will vanish as a variable and it will become a numerical number. It will, that weight will be added to, multiplied with each and every control point x y z, and it will be giving me x y z of the point. This is the way in which we proceed. So, once this is clear to you, I am sure after that if you take up Bezier surfaces in more detail, I am sure you will be able to follow it, because after this comes derivation of a Bezier curve to find out tangent, where you will be deriving it with respect to u, and u will be derived here, control points will be left over, they will not be affected, all these things will be coming automatically. So, if you can start from this point, if you still have problems, please get in touch with me over the forum, I will try to help you as much as possible. Okay. So, let me see whether some other questions have come in. How much time do we have? Okay. We have come to the end of the 1 hour discussion. If I get a feedback from other students or you people only that you want more of these interactive sessions, we can definitely arrange for it before the holding of the final exam. But for the time being, let us close down here. Let us review our improvements in your concepts and whether it has helped you. If required, we will definitely meet again. So, till then, thank you very much for listening in.